Hi, I'm Alfonso Lagares, a student in Professor Fenton's Physics 2211 class, and this is my Lab 2 report where I'll be studying the motion of a falling object. First, I'll introduce the concept of drag and why it is important to understand. Then, I'll explain how I collected this lab's data using Tracker and a computer model in Python. Then, I'll analyze and discuss this data, and finally, I'll give a short conclusion and evaluation of the lab. This lab focuses on objects that experience turbulent drag. In other words, that experience friction with a fluid. Air is a fluid, and thus everything that moves inside the Earth's atmosphere experiences drag. Drag is caused by two phenomena, skin friction drag and pressure drag. Skin friction drag is caused by fluid particles that collide against an object's rough surface, applying a force opposite to the velocity of the object. Pressure drag, on the other hand, is caused by the compression and expansion of the fluid by the object as it travels through it. As it moves, the object compresses the fluid in front of it, while at the same time creating an area of low pressure in its wake. This difference in pressure creates a force that opposes the motion of the object. These two phenomena are grouped into a single force, the drag force, which is directly proportional to the square of the velocity of the object. The force and the square of the velocity are related by a constant b, known as the drag coefficient. Objects that are falling and are affected by drag will have two forces acting on them, the force of gravity and the force of drag. There will be a given velocity where these two forces will be equal and the object will reach a final maximum velocity, also known as terminal velocity. The terminal velocity is dependent on the mass of the falling object, the drag coefficient, and the gravitational acceleration. Understanding drag is critical, especially when dealing with objects that move inside the atmosphere, such as vehicles like planes or cars. The force drag applies on them has to be accounted for in order to fully comprehend their motion. In order to fully understand the drag force, I used Tracker to extract data from a video of a bunch of coffee filters falling from a height. In this case, the studied system consisted of the coffee filters, the floor, and the earth. I dropped the coffee filters from a height of 2.3 meters and recorded their position over time using Tracker, trying to keep the camera perpendicular to the floor and the wall in order to avoid parallax error. This data was then imported into Excel. Going on to the model, I used GlowScript to simulate the fall of the coffee filters. The object is represented by this ball object, and a trail and origin are assigned to it, as well as arrows that represent the forces of gravity and drag. The system is then given a mass, which for the coffee filters is 0.114 kilograms, an initial position at 2.3 meters above the origin, and an initial velocity of 0. I also defined the acceleration due to gravity and the drag coefficient, which was calculated using this formula, derived by setting the force of gravity equal to the force of drag. The terminal velocity used to calculate the drag coefficient was taken from the terminal velocity observed in the tracker data. The simulation is run for 0.9 seconds, the time the filters took to reach the floor. The gravity and drag forces are calculated and added to find the net force of the object, and Newton's second law is applied to update the velocity and position of the object. All arrows and graphs are also updated, and the position and velocity are printed to a console for exporting them to Excel. The result is this animation of the object falling, plots of the object's position and velocity, and the actual position data. This data was then exported to Excel in order to study it more closely. I also ran the simulation without including the force of drag, which gave me two models to compare the observed data with. Comparing the observed and predicted motion of the filter paper, we can conclude that the model was accurate at predicting this kind of motion. Furthermore, we can conclude that not accounting for the drag force would have been incorrect, as the predicted motion of the object without accounting for drag has a significant deviation from the observed position. There is some systematic error in the simulation's precision, probably due to the inaccuracy of the mass of the filter paper, which was difficult to measure due to its small value. Furthermore, the drag coefficient can be another source of error, as its calculation depends on the observed terminal velocity, which is difficult to measure due to the noisiness of the experimental velocity data. In order to improve the model's accuracy, I believe these two variables should be measured more precisely. To summarize, the observation and model produce similar data, but the model's accuracy could be improved by more precisely measuring the mass and coefficient of drag. Out of the two models used in this lab, the one that predicted a terminal velocity was the model that accounted for the drag force, as it predicted a decreasing net force eventually reaching a point where the net force of the object is 0. This means that the velocity will stop changing, like in the graph, at which point the object will have reached its terminal velocity. If the object was given an initial velocity, its terminal velocity would not change, as the terminal velocity of the object only depends on its mass and drag coefficient. Furthermore, simulating the object with an initial velocity shows that the terminal velocity remains the same, the only difference being it is reached earlier in the motion.